Here we've got three 1.9 microcoulomb charged particles, on an equilateral triangle with side length 0.4 meters. And the question is, what is the energy of the system? Now I think a fair question and response is, what does that even mean? What is the energy of the system? So this is a certain kind of electric potential problem. I don't think I did one in class. Hopefully you figured it out on the homework, but if you've forgotten, here's a quick review before we get to the exam. So what the energy of the system means, it really is how much energy does it have. And one way to think of that is if you released it, these particles would fly away from each other and get so far apart they would have no interactions anymore. And then how much kinetic energy would they have? You're basically converting all your potential energy to kinetic energy. An easier way to think about it is if you have these particles infinitely far apart with no interactions and no electric potential, really, because they're so far, and what if you had to bring them all in and push them together to make this assembly? How much work would you have to do? The external work you would do would be how much potential energy you're creating when you put them together. So that's kind of what it means, and here's kind of how you do it. You kind of do it in steps. I think of it this way. One is the three charges are infinity apart. Right? So the potential energy is zero. Because they're so far, you put infinity in the kq over r terms, and they're all zero. And then the second step is bring one into position. And think about how much work did you have to do to bring that first charge into position. We'll go ahead and draw it here. There it is, 1.9 times 1.9 microcoulombs. And this will be the rest of the triangle here once we finish it. So how much work did we have to do? We didn't have to do any work. When you first bring this charge from infinity to here, there's nothing creating a potential here, nothing for it to push against, so U is still zero, equal to zero. Haven't done any work yet. 3. Bring the second charge. Okay, so now we have the second charge at infinity. We bring it to here, and it is Q2, and I won't write it, but it's also 1.9 microcoulombs. Now we're pushing against something here. So the energy of Q2, or the energy to do that, is the charge Q2 times the delta V. Right? Okay, so Q2 is 1.9 times 10 to the minus 6 coulombs, and then potential final minus initial. The initial potential that was zero because it was at infinity, and we brought it up to here. So what's the potential here? Well, it's a certain distance from that charge. It's in the potential created by that charge. So that is K, 9 times 10 to the 9. That charge, which is also 1.9 times 10 to the minus 6. Right? Over the separation, they gave us is 0.4. You multiply that out, and you get 0.0812 joules. 81.2 millijoules, if you're keeping up with it that way. Okay, so part of the energy to assemble this is 0.0812 joules. But now, let's go to step 4. Step 4 is bring the third charge. Okay? Third charge, we have it at infinity, and we have to push and do work and push against these two to get it to here. Right? We had to do a lot of work to get it there, because we had to push against this one and this one. And if you think about the potential each one of them is creating, since this triangle is equilateral, it's really the same. Right? It had to push against its charge, which is the same, has to push against K, same charge, Q, over the same distance, 0.4 meters. So because all these charges are the same, and because the distances are all the same, and the triangle is equilateral, really we know that the answer to this one is just one interaction here and one here, so it's twice that. So delta U for this part, we'll call this delta U2 for charge 2, and delta U3 for charge 3. I don't want to write it all out again. It's 0.0812 joules times 2. I set up the equations, it would just be two of these. All right. So what was the question? Yeah, so what does the energy to assemble this thing? So then the delta U total is, well, it's just 3 times 0.0812 joules. And you do one of them here and two of them there. 3 times 0.0812 joules, and the real answer when you do that is 0.244 joules. And that's the correct answer. So thinking of it this assembly way, sometimes it bothers people that we feel like we didn't do anything about this one. Well, remember, we got to bring that one in for free. It's because of the order that we brought them in. There was nothing to push against when we brought this one in. And it's not doing nothing, it's the one that pushed against this one and the one that pushed against that one. Another way to think of it is to take the final structure and just look at it and just count the number of bonds or interactions. Right? So here there are basically three interactions. So you just multiply K, Q, Q over R to get an energy for every line you can draw between two charges. If there were 4, there'd be a lot more, right? There'd be 1, 2, 3, 4, 5, 6. So it goes up fast when the number of particles gets more complicated. But here you could have just done that. You would have said 1 plus 2 plus 3. So you can solve these either way. Another way these get interesting is they set it up like this. They say, we let it go. The particles fly apart. How fast are they going? That's a case where you calculate this energy first, and then you set it equal to 1/2 mv squared for each particle,